When a major physical incident strikes an industrial site or defense installation, the network rarely fails because of a severed cable. Watch what happens to a facility's network when a physical shockwave hits. Hundreds of sensors, cameras, radar, acoustics, detect the anomaly and react simultaneously. This creates a paradox in massive sensor integration. Systems collapse under correlated bursts, a synchronized spike in data occurring at the exact moment the system is most critical. Cameras automatically slew to the target, AI inference engines spin up, and high-resolution raw video begins replicating to redundant servers. Every edge node flashes and dumps its payload toward a single central fusion point at the exact same time. The arithmetic sum of these simultaneous reactions instantly exceeds the available link capacity and egress queues. The exit pipeline is fixed, but the incoming volume is massive, forcing packets to back up. Standard Quality of Service, or DiffServ, tries to manage this by reading transport packet headers, but standard QoS is blind to mission semantics. A strict priority queue sees a priority tag, but it doesn't know if that packet contains a fresh radar track, an obsolete video frame, or a forged mark from a compromised device. As these queues fill, buffer bloat sets in. Packets aren't necessarily dropped right away, they are delayed. In a sensor fusion loop, a delayed observation corrupts the entire operating picture with stale data long before an alarm ever declares a network outage. Deterministic network behavior requires strict mathematical boundaries, not just theoretical priority rankings. This chart plots the ingress-arrival curve, showing the mathematical relationship between incoming burst size, admitted sustained rate, and time. It demonstrates a strict rule: you cannot offer deterministic latency bounds against an unbounded data source. This brings us to the joint class feasibility constraint. A token bucket shaper acts as a gatekeeper. It enforces the admitted envelope rate, ensuring that the sum of all admitted sensor rates never exceeds the usable link service. Excess load is discarded before it ever reaches the physical buffer. During a correlated event, hundreds of sensors react at once. If that traffic isn't actively shaped and policed at the edge, the influx will inevitably violate this feasibility constraint. Conventional network routing relies on passive queue management. It waits for the physical buffer to actually fill up and overflow before it starts dropping packets. Preventing buffer exhaustion requires an AI quality of service contract. The system must forecast the queue, limit the incoming bursts, and govern the flow of data based on its actual operational value before the physical capacity runs out. This PTCP-SARAHAI diagram traces the pipeline from point sensors to the slow path. To survive bursts, the architecture isolates a hot path exclusively for critical state like radar tracks. Heavy bulk payloads are routed to the slow path and deferred. The system maps every piece of data into precise service classes. These range from AIQ0, strictly reserved for critical timing and alarms, down to AIQ5 for bulk exports. Devices cannot simply assign themselves top priority. Every priority mark must be cryptographically authenticated at the edge adapter, preventing a compromised sensor from spoofing its way into the critical queue. By enforcing this strict separation, an unshaped, opportunistic 4K video stream is physically barred from consuming the bandwidth required to deliver an active radar track. When a chaotic physical event occurs, separating the compact decision state from the heavy raw evidence keeps the network deterministic. The system maintains continuous operational awareness without choking on its own data. Even with strict admission controls, a massive swarm event can still push admitted traffic toward the absolute physical limits of the hardware. So, how does the system react? This chart maps the certified operating envelope from normal operation to the outside envelope. As load crosses into the guarded and constrained zones, the system executes a quality ladder, systematically shedding lower value fidelity to protect the hot path. This means reducing camera frame rates, shifting to region of interest snapshots, or pausing non-urgent maintenance replays. If traffic hits the red outside envelope zone, physical saturation is imminent. Here, the system must actively reject new, lower priority work and explicitly inform the operator that their awareness is degraded. Rather than suffering an uncontrolled network collapse where everything fails at once, PTCP-SARAHAI executes an explicit, mathematically governed degradation process. It sacrifices resolution and background tasks to ensure critical tracks survive. Standard routing protocols like equal cost multipath evaluate routes based on logical distance or hop counts. In a physical AI network, this abstract logic is dangerous. Two network routes might appear perfectly separate on a logical graph, But in reality, those distinct cables might share the same physical trench, draw from the same power feed, or run through the same cooling loop. If that trench is severed, both logical paths die simultaneously. This topographic mission graph maps connections between edge, core, and fusion nodes, enriching the network with physical terrain and trust boundaries. To navigate, geodesic routing weighs the paths using multiple constraints, finding the minimum mission cost path to prioritize reliability. These are hard constraints. A route cannot be selected if it violates a latency deadline, a security clearance, or a zone isolation policy, even with infinite bandwidth. The geodesic formula continuously scores every candidate path, factoring in predicted queue latency, remaining capacity, topological risk exposure, and the current security posture. True determinism requires routing algorithms to integrate the physical reality, the built environment, and the operational risk of specific conduits into their path selection. Protecting bandwidth and physical routes ultimately serves one goal: minimizing the age of information. This animation visualizes the delay propagation formula for tracking a moving target. Notice the tight bounding box representing our confidence in the target's location. As the time delay between the sensor and the AI increases, that area of covariance, the mathematical uncertainty, rapidly expands outward. If a packet arrives late and drops into this expanded area of uncertainty, it fails to correct the tracking model. Downstream AI processes propagate this noise, resulting in false precision and a completely skewed trajectory. This is why the architecture is programmed to drop expired copies rather than delivering them late. A silent, late delivery is dangerous because the fusion engine might mistake obsolete data for current truth. Strict delivery deadlines provide the foundational conditions required for AI accuracy. All of this mathematical routing and queue management directly impacts the human operators sitting in the Security Operations Center. This diagram maps the 6-step SOC closed-loop mission workflow. Because automation strictly handles Step 4, protecting the routes, the human operator is free to focus purely on Step 3, correlating data, and Step 5, making decisions based on verified truth. If wide-area network connectivity drops, or the central controller goes offline, the edge nodes shift into a fail operational posture. They execute bounded local autonomy, relying on last known good policies to spool evidence locally and maintain critical tracking. Software cannot magically generate infinite capacity. But by implementing AI-aware queuing and separating state from evidence, a facility guarantees that within its measured envelope, the most critical data will survive the crisis.